I'm going to cover two types of problems in this video. One is specific heat capacity of a metal, and the other one is heat of dissolution. So I'm going to cover the specific heat problem first. Now what this problem says is a 12.48 gram sample of some unknown metals heated to 99.00 degrees Celsius. It's then dropped into 50.00 milliliters of water that is at 25.00 degrees Celsius. The temperature of the water rises to 28.10 degrees Celsius, assuming no loss of energy to the surroundings. What is the specific heat of the metal? So since it's asking for specific heat of the metal, the overall equation that we have to get to is specific heat of the metal equals Q, which is heat of the metal, heat content, divided by the mass of the metal times the temperature change of the metal, so delta T of the metal. So all of those things in that equation have to be for the metal. Now, the mass of the metal and the delta T of the metal we can get from the problem pretty easily. The mass is listed 12.48 grams. Now, it doesn't specifically say the final temperature of the metal, but the initial temperature is 99.00 degrees Celsius. The final temperature of the metal is going to be the same as the final temperature of the water, which is 28.10 degrees Celsius. They'll end up at the same temperature. So what we have to solve for is the heat content of the metal, Q metal. Now, we can't do that directly. So what we have to do is calculate the effect the metal has on the water. So we're going to first figure out how the heat content, the Q of the water, changes. And when you think about this from the metal's point of view, the metal is releasing heat. So we should expect Q metal to end up being negative because it's starting out at 99.0 degrees Celsius and going down to 28.1. So it's lost a certain amount of heat. The water, we should expect the Q term, the heat term for that, to increase because it's going from 25.0 up to 28.10. So we're going to figure out Q water. So we know the specific heat of water, that is a constant. We know the mass of the water, and we know the delta T of the water, or we can figure that out. So specific heat of water is 4.184 joules per gram degrees C. The mass of the water was listed as 50.00, well, the volume was 50.00 milliliters, which is the same as a gram, because the density of water is 1.0 grams per milliliter. The delta T of the water, you do final minus initial, so you do 28.10 degrees Celsius minus 25.00, right, because it's final minus initial. This is the final temperature, this was initial. Do the subtraction first, because when you subtract, you go by decimal places, and they both have 2 decimal places, so the answer should have 2, and that gives you 3.10 degrees Celsius. Now, when you multiply, you go by the least number of significant digits, and when you multiply this out, you get an answer that's 648.52 and a whole bunch of numbers. Now, the grams cancels out. The degrees Celsius canceled out, and what you're left with is joules. Now we want to round this off to 3 significant digits because the 3.10 has the least number of significant digits, and when we multiply, we go by significant digits. So that becomes 649 joules. Now that kind of makes sense because we said the water was increasing in heat, and you know that because the temperature goes from 25 up to 28.10. So this is telling you that we have a positive change in heat for the water. So if Q water equals 649 joules, that means that the Q of the metal is the exact opposite. If the water absorbed 649 joules, the metal released 649 joules, so we make that a negative. So that becomes negative 649 joules. And that's what we were looking at for up here, this original equation, this Q metal. So now we have all the information we need to figure out the specific heat of the metal. So Cp of the metal equals that negative 649 joules divided by the mass of the metal, which was 12.48 grams, multiplied by the delta T of the metal. Remember, delta T is final minus initial. the metal ended up at 28.10 degrees Celsius, just like the water did, and it started out at 99.00 degrees Celsius. Again, do the subtraction first. Go by the least number of decimal places, so that is negative 70.90 degrees Celsius. Now, if you multiply this all out, what you should get is 0.73347 and a whole bunch of other numbers, and it's joules per gram degree C. Now we go by the least number of significant digits, which is this negative 649 is 3 significant digits. So we round our answer off to 3 significant digits, 0.733 joules per gram degree C. That ends up being the specific heat of the metal. So figure out how the metal affects the water. Use that number to figure out the specific heat of the metal. Okay, the next problem I'm going to do is heat of dissolution. That one tends to be a little more involved, a little longer. Alright, so we have this problem here. It's also called enthalpy of solution. If you take potassium chloride, an 8.952 gram sample of it, and you dissolve it in 40.00 milliliters of water in a calorimeter, the temperature decreases from 32.6 to 22.6 degrees Celsius, so it goes down by 10.0 degrees Celsius. What is the molar enthalpy of solution for potassium chloride? Assume that the solution has a specific heat capacity equal to that of water. So I'm asking for, the overall thing I'm asking for is molar enthalpy for KCl. Now, anytime you're looking for molar enthalpy, that is delta H. The equation for delta H is Q of the substance, that's like saying the chemical, that's the potassium chloride, divided by the moles of that substance. You should get the units of kilojoules per mole. The mole is easy to figure out. That's like what we've always done. You take the mass of potassium chloride, you use the molar mass off the periodic table, you convert it to moles. The kilojoules takes a little more effort. We have to figure out Q of the substance. Now, it's kind of like what we had to do with the specific heat capacity problem. We can't figure that out directly. We can't get like a thermometer in the bonds of that reaction or anything like that in the bonds of the chemical. So we have to figure out, how did this chemical affect the surroundings? So you can think about it as Q surroundings, which is really the numbers, the values for the solution. Now what we get is the specific heat. Now in the problem it says assume the solution has a specific heat capacity equal to that of water. So we know what that is. We need the mass of that whole solution, and we need the delta T. One of the things that people forget to do with this is that when we're taking the mass, it's of the solution, because now the difference between this and a specific heat capacity problem is this solid, when we put it in, it dissolves. So when you see the word dissolve, that's telling you you are forming a solution. And a solution has two parts. It has the solute, that is the substance that gets dissolved, and it has the solvent, that is the substance that does the dissolving. So when you work with the solution here, you have to add the solute, which is at 8.952 grams of potassium chloride, and the 40.000 milliliters of water. So we have to remember to multiply that out. If you're going fast, that's an easy part to forget. So we get the specific heat of water is 4.184 joules per gram degree C. That is a constant. That doesn't change. Now the mass of the solution, I have to add those numbers up. Now 40.000 milliliters is the same as 40.000 grams. So that makes that nice and easy. They both have 3 decimal places. And remember, you go by decimal places when you're adding. So that's 48.952 grams. And now we do delta T. Remember, it's final minus initial, and it decreases in temperature. So you're going from 22.6, well, you're going from 32.6 to 22.6. So now you do final minus initial. So you do 22.6 minus 32.6 degrees Celsius. And what you get as Q surroundings is a negative number. Negative 2,048 0.15, and a whole bunch of numbers after that. The grams are going to cancel out. The degrees Celsius will cancel out. What you'll be left with is joules. Now, before we move any farther, it's worth thinking about exactly what we're looking for in here. We know that the temperature decreases from 32.6 to 22.6. So from the chemical's point of view, the delta H for this, we want to figure out what the sign is going to be along with a number. So if temperature decreases, that's telling me that it's an endothermic reaction. The chemicals themselves took energy away from the surroundings, and since we measure the surroundings, that's why we see it as a temperature decrease. So delta H, by the time we get to the end, since it's endothermic, we should expect delta H to be positive. But what we just calculated is the heat, the Q of the surroundings, the solution itself, went down by about 2,000 joules. Now that makes sense. We measure the surroundings and the temperature decreased, so we should expect to see a negative heat value for the surroundings. Now we want to eventually get to kilojoules. So what I'm going to do is just convert this to kilojoules right now. So just going from joules to kilojoules, and we want to match the number of significant digits. When you do the subtraction, that's a negative 10.0, matching the decimal places. So that's one decimal place, but now when you multiply, you go by significant digits. That's 3 significant digits, so you get a negative 2.05 kilojoules, and that is Q of the surroundings. But if Q of the surroundings equals negative 2.05 kilojoules, then Q of the reaction, the actual substance, I'll just write RXN for reaction. You can also think about it as Q of the substance, whichever way makes more sense to you. That ends up being a positive 2.05 kilojoules. If the surroundings went down by 2.05 kilojoules, that means the substance, the chemicals themselves, the reaction, went up by 2.05 kilojoules. They took that 2.05 kilojoules from the surroundings. Now the next thing we have to do, and I'm going to label this as all part 1. The next thing we have to do is figure out the mole. We just figured out the kilojoules. We have to figure out the moles now. So the moles is like what we've always done doing a molar conversion. 8.952 grams of KCl. Since you start off with grams of KCl, they go on the bottom. We're converting it to moles, so moles goes up top. It's always 1 mole is whatever you get off the periodic table. Now, potassium is 39.1. Chlorine is 35.5. You add that up, and that's telling you that if you have 1 mole of potassium chloride, you would have 74.6 grams of it. You do this math, matching the number of significant digits, which is 4. You get 0.1200 moles of KCl. And that's this part. So now we have both of these numbers figured out. So we just have to plug it into that equation. So the last thing here is delta H equals the Q of the substance, which we figured out over here, positive 2.05. I'll just write positive just to be very thorough. Kilojoules. Divided by the moles that took part in this reaction, which is 0.1200 moles. You do the math for that, you should get 17.1 kilojoules per mole. So that's telling me if I had a mole of potassium chloride and I dissolve that in water, I should expect to get a positive change in energy and enthalpy of 17.1 kilojoules. Now what I saw was a lot less than that. It was only about 2.05, and that's because I had a lot less than a mole. All right, now if we were going to write this, it doesn't say it in the problem, but if we were going to write this as an equation, include the heat term in the equation, what we ended up doing is potassium chloride, that was a solid. We had a positive delta H, so that means it's endothermic. When it's endothermic, heat ends up being on the reactant side. So that 17.1 kilojoules, and it's per 1 mole, is a reactant. That causes this potassium chloride to dissociate. You get the ions. Potassium has a positive 1 charge, and since it's dissolving, it ends up in the aqueous phase, so you have AQ for aqueous, And then we also have chloride ion.